We will introduce the concept of an integral by thinking about the area under a curve. The integral and derivative will turn out to be each other's undo buttons, as stated in the first and second fundamental theorems of calculus. We will close with a change of variables rule that allows us to recognize disguised forms of patterns from integration tables. As with differential calculus, integral calculus is credited to Newton and Leibniz. Consider a function with a plot such as this. Shade a region bounded by the vertical lines x equal a and x equal b, by the x-axis, and by the plot of f on x versus x. How many square tiles can fit in the orange shaded region? Use the height of f on a to draw a rectangle extended toward the right. Draw another rectangle picking up from where the last one stopped, and another one, and another one. Look, for example, at the rectangle with left-hand corner at x equals a plus delta x and height f on a plus delta x. Its area is f on a plus delta x times delta x, which is one of the terms inside this sum. The orange shaded area is approximated by the sum from k equals 1 to b minus a, that stuff over delta x, of f on some stuff times delta x, where the stuff is a plus k minus 1 copies of delta x. The viewer may pause the video to verify that this corresponds to the sum of the areas delta a of a bunch of rectangles placed between x equals a and x equals b. Does this sum make sense with all possible values of delta x? Using smaller delta x would produce a finer approximation to the orange shaded area. Shrinking delta x again gives us a collection of turquoise rectangles that even more closely hugs the yellow curve. We define the area of the orange shaded region as the limit as delta x goes to 0 of the sum of areas of rectangles. We look at an unending succession of sums of rectangular areas, with widths delta x becoming ever smaller, but in every situation still being finite. If that succession of sums has a limiting value, it is called the area under the curve between x equals a and x equals b. We call this object a definite integral. The smooth S symbol that resembles a sound hole on a violin is read integral. This expression is read, the area A equals the integral from x equals a to b of f on x dx. The smooth S is meant to remind us of a notion of a sum, and the dx is meant to remind us of the notion of delta x shrinking. The smooth S and dx symbol should be considered two syllables that have meaning when combined, but not when written in isolation. We wrote a differential dx. In the module on differentiation, we were warned to avoid thinking of differentials as numbers in their own right. Instead, we were told to look for notions of coordinated shrinkage whenever we saw a differential. Please pause the video to think about what is coordinately shrinking with delta x. The answer is not stated in this video. As an example, we will deduce the area under a slanted line. This is the plot for the function with association rule f on x equals 2x. We want to calculate the area of the orange shaded trapezoid into which these progressively finer rectangles are melting. The trapezoid consists of this red rectangle and this purple right triangle. The height of the rectangle is 2a. The right-hand wall of the trapezoid has height 2b, so the height of the purple triangle is 2b minus 2a. Let's walk through the combined area of the rectangle and triangle. The rectangle has area equals height times width, which is 2a times b minus a. The right triangle has area equal to half times the height times the width, or half times quantity 2b minus 2a times quantity b minus a. Cancel these factors of 2 out. Positive and negative copies of a times quantity b minus a cancel each other, and the remaining terms nicely collect as quantity a plus b times quantity b minus a. Distributively multiplying or foiling, we find that the area of the trapezoid is b squared minus a squared. Hence, the integral from x equals a to b of f on x dx, for this f on x anyway, is b squared minus a squared. If we regard the left-hand boundary, that's x equals a, as fixed, then the derivative of uppercase A with respect to b, evaluated at x, is 2x. This happens to be the association rule with which we began, f on x equals 2x. This is no accident. The derivative is the undo button for integration. Do you remember why? The answer is about to follow. The first fundamental theorem of calculus is the statement that the derivative undoes integration. We want to take the integral from x equals a to b of f on x dx and show that when this object is differentiated with respect to its endpoint b, and then evaluated at b equals x naught, we get back the original function evaluated at x naught. Consider a function with a generic plot like this. We want to look at successively small differences between areas evaluated under the curve. The derivative of the area, or of the integral, is the limit as delta x approaches 0 of the fraction with numerator area evaluated at x naught plus delta x minus area at x naught over the denominator delta x. Here is some reference left-hand boundary x equals a. And here is x naught. The area evaluated at x naught is indicated in orange shading. The area evaluated up to x naught plus delta x includes the area shaded in orange and an additional area shaded in red corresponding to the area under the curve between x naught and x naught plus delta x. The difference between the area evaluated at x naught plus delta x and the area evaluated at x naught is the area of the sliver shaded in red, which can be thought of as the area of this purple rectangle and this green wedge. Move stuff up the board for more space. As we shrink delta x, the purple rectangle and green wedge both get smaller in width. However, the green wedge also gets smaller in height. It's doubly small and can be neglected. The area of the red sliver is thus approximated by the area of the purple rectangle alone, which has height f on x naught and width delta x. In other words, it has area f on x naught times delta x. Divide both sides by delta x. Assuming the plot of interest is not horribly jagged, we repeat this line of argument for smaller and smaller but all the while finite delta x's, expecting the ratio of differences of area over delta x to become arbitrarily close to the derivative dA dB evaluated at x naught, and expecting the rough equality to become arbitrarily accurate. Since uppercase A is the integral from x equals a to b of f on x dx, we have confirmed the expression we sought to show. The derivative of an integral spits back out the original function's association rule. Not only is the derivative the undo button for the integral, according to the second fundamental theorem of calculus, the integral is the undo button for the derivative. We want to show that the integral from xd equals a to b of df dx at xd equals f on b minus f on a. The integral of the derivative of a function equals the difference between the function evaluated at the final endpoint of the integral and the function evaluated at the integral's initial boundary. We draw both a plot of f on x versus x and a plot of its derivative df dx, calling the points at which we evaluate the derivative xd. The integral is the area under the plot of df dx between x equals a and b, which could be approximated using a collection of rectangles. Look at the rectangle at x naught. Its height is df dx at x naught, its width is delta x, so its area delta a is df dx at x naught times delta x. Hugging the plot of f on x versus x with a staircase, we identify a right triangle with left-hand corner at x naught, drawn with the same width delta x as the rectangle below. If the triangles are small, the ratio between delta f and finite delta x is close to the limiting value df dx at x naught. So the height of the triangle is delta f, which is approximately equal to df dx delta x. Notice that this height delta f roughly equals the rectangular area delta a because both are basically df dx delta x. The area of this rectangle is equal to the height of this triangle, and likewise for the rest. Because the heights of the triangles correspond to the areas of the rectangles, adding the heights of the triangles is a proxy for adding the area of the rectangles. Add the heights of the right triangles vertically. They equal the difference between the height f on B and the height f on A. Again, adding up the heights of the golden arrows is equivalent to adding up the areas of the turquoise rectangles. We have demonstrated that integration undoes differentiation, as we sought to show. As with derivatives, we often memorize patterns we have deduced so that we need only derive them once. Commercial integral tables look like this. These patterns are somewhat similar to what we have seen in the last couple of modules. We just talked about how derivatives and integrals undo each other, so it's not surprising to see in these table entries for integrals relationships that look familiar from our work with derivatives. At the same time, the formatting on these expressions looks a little strange. Let's walk through this abbreviated notation. For example, using a power law, a function with an association rule f on x equals x taken to the nth power. We already studied the power rule for derivatives, df dx at xd equals n times xd taken to the n minus 1 power. According to the second fundamental theorem of calculus, the integral of a derivative spits back out the original function's association rule, more specifically the difference between the original function evaluated at the final and initial bounds of the integral. So where the original association rule gave x to the n, we will now evaluate f on x at b to get b to the n, and f on x at a to get a to the n, and take the difference b to the n minus a to the n. This is the longhand version of this integration pattern. Relabel the top integration bound or integration limit x instead of b. Now suppress the subscript and superscript adorning the smooth s, suppress the subscript d, and replace the minus a to the n with positive c, which just stands for some constant. We now have the first entry in the integral table. The abbreviated patterns can be called indefinite integrals, as opposed to definite integrals, because the initial and final bounds of the areas of integration are not specified. There is an alternative way to present the standard format of integration tables using the notion of an antiderivative. Instead of maligning the indefinite integral as the result of forgetting to write down a lot of symbols in a definite integral, one usually says that, in the context of an equation lacking beginning and end points, such as integral without a superscript without a subscript of lowercase g on x dx equals capital G on x plus c, the curvy s indicates merely that taking the derivative of capital G gives lowercase g. This approach does not require one to discuss the notion of area under a curve. Many of the rules in integration tables can be applied more broadly if we know about the change of variables trick. We want to show that we can relate two integrals written in terms of two sets of variables. The integral from x equals a to b of g on f on x df dx dx equals the integral from f equals f on a to f on b of g on f df. The variable x appears explicitly on the left-hand side but not on the right. The integral in which x appears explicitly can be approximated using a sum of areas. Please pause the video if it is unclear how the integral and sum are related, letter by letter, punctuation mark by punctuation mark. We plot f on x versus x and g on f on x versus f on x on a three-dimensional set of axes. Here is a point x0, and here is a right triangle with horizontal run of length delta x. If the triangle is small, the ratio between delta f and finite delta x is close to the limiting value df dx, so delta f is approximately df dx delta x, which corresponds to a vertical interval along the f-axis. The value of g on f on x evaluated at the tail of the yellow arrow is g on f on x0. The area of the rectangle is the product of its pink length, g on f on x0, times its yellow length, which is delta f, or more explicitly, df dx times delta x. These three objects, g on f, df dx, and delta x, are those objects that appear within the sum. Specify boundaries at x equals a and x equals b to obtain a bunch of yellow arrows. Generate corresponding rectangles and add their areas to get an approximation of the pink shaded area. Calculating the area of the pink shaded region is equivalent to performing the sum from k equals 1 to b minus a, that quantity over delta x, of g times df dx times delta x. The points x equal a and x equal b on the x-axis correspond to the values f on a and f on b on the f-axis. The pink area is the region bounded by f equals f on a, f equals f on b, the f-axis, and the curve g on f versus f. This is the integral from f equals f on a to f on b of g on f df. The integral of g on f on x, df dx is equivalent, when boundaries are specified appropriately, to the integral of g on f df. As an example, suppose you are confronted with the integral from theta equals a to b of 3 times the square of sine on theta, cosine on theta, d theta. To what does this integral evaluate? Let f on theta stand for sine on theta, then the derivative of sine, that's df d theta, equals cosine on theta. We are being a little sloppy by evaluating the derivative at theta rather than at theta naught. Everywhere we initially saw sine, now instead write f, and where we saw cosine, write df d theta. According to the change of variables rule, the integral from theta equals a to b of 3 times the square of f on theta, df d theta, is equal to the integral without theta appearing explicitly, namely, the integral from f equals sine on a to sine on b of 3f squared df. But that's just an example of the power rule for differentiation. Evaluating f cubed at f equals sine on b and sine on a, and taking the difference, we obtain the value of the integral.